Hi everyone, this is Latya from Department of CSC, SNS College of Technology. We are going to see about operating system deadlock in this session. In previous session, we have already seen what is a deadlock and what are the causes of deadlock and what are the characteristics of deadlock. And under that, we have seen methods of handling deadlock. Under the methods of handling deadlock, there are totally four. That is of deadlock prevention, avoidance, detection, and recovery. Under prevention and deadlock avoidance, we have already seen what are the conditions of deadlock prevention and what are the methods of deadlock avoidance in previous sessions. In today's session, we are going to see about deadlock detection followed by deadlock recovery. Okay, in this deadlock detection, we are using deadlock detection algorithm. That algorithm examines the state of the system to determine whether the deadlock has occurred in that system, and we will be using a separate algorithm for recovery in the system from that deadlock. These are the two steps followed in this. As we have seen the scenario, this scenario comes under which allows the system to enter into the deadlock and after that getting recovered from deadlock. First, in deadlock detection, we are taking account in the single instance resource and followed by multiple instance resource. For single instance resource, the deadlock detection is performed by wait for graph. Wait for graph is nothing but it is similar to resource allocation graph. We have seen the resource allocation graph previously, right? Resource allocation graph is nothing but a pictorial or graphical representation of the system resources and the processes which holds that resources, in which process is denoted by P and the resource is denoted by E, R, whereas each resource and process are getting connected by the edges of request edge, claim edge, and allocation edge. Do you remember that RAG? With that RAG only we will be constructing the wait for graph. Wait for graph is nothing but it contains only the process. RAG contains the process as well as the resource. In this wait for, we contain only the process, the resource will get eliminated. For example, if two processes are interlinked by a resource, then that resource will be removed and the process will be denoted by an arrow mark. For example, if the process P1 is holding the resource of R1 and the process P2 is requesting for R1, after P1 releases the R1 only, the R1 will be get allocated for P2, right? So the process P1 will be directly allocated to P2. In that situation, whenever the process P1 gets completed, then the process P2 starts its work. This is the indication of process to process. That is why it is indicated as PI to PJ, whereas PI is waiting for PJ. Periodically, it invokes the algorithm for searching whether the cycle is forming in a graph. If there is a cycle exists in a graph, as we have discussed earlier, if a cycle exists, then there is a possibility of occurrence of deadlock. That too, if it is of a single instance resource, there is a compulsory state where deadlock get occurred. Then if it is of multiple instance, there is a possibility of occurrence of deadlock, or else a deadlock might not be occur also. An algorithm detects the cycle in the graph requires n power 2 operations, where n is the number of vertices of the graph. Okay, here it is the graph. First one represents the resource allocation graph, whereas second one represents the wait for graph. As I have discussed earlier, in this the resources R1, R3, R4, R2 and R5, which was interlinked between all these processes of P1 to P5, is getting removed and it is directly given for wait for graph. If the wait for graph forms a cycle, then there is an possibility of occurrence of deadlock in that single instance of resource. Okay, let's see briefly about the construction of wait for graph from resource allocation graph now.